In lecture 14, we're going to learn how to justify the fundamental group of the punctured plane and the fundamental group of the circle, something that we have alluded to based on our intuition in the previous lectures, but we never actually proved. Now, these go together. The circle and the punctured plane, they go together because they have the same homotopy type. So let's just recall the punctured plane is homotopy equivalent to the circle, because the picture that we've talked about, and you also had this problem on your homework, that the circle sits inside the punctured plane, and then you can map every point on the circle. Every point in the punctured plane can be mapped to the circle by moving along these rays, like that. And that mapping from the punctured plane to the circle gives us a homotopy equivalence. So because of this, the fundamental group of the plane, let's say at 1, at some point, is going to be isomorphic to the fundamental group of the circle at 1, or at any other point. So the reason why I'm putting these together is because it's more convenient to draw pictures in the punctured plane than it is to draw pictures on the circle. If you draw pictures on the circle, everything is like one-dimensional, so you cannot see anything. But the pictures do look nicer in the punctured plane. But when it comes to doing the proofs, it's more convenient to work with the circle because it's like notation-wise, it's simpler. It's a simpler object to work with. So that's what we're going to discuss. And let's say what the main theorem is. Before I write down this theorem, there's something interesting that happens, and that is this is going to be the one computation, and I mean these are really equivalent computations, but this is going to be the one computation where very specialized methods will be required to get it to work out. All of the other computations that we end up doing after this, where we compute the fundamental group, all of those computations, interestingly, there will be methods, quick methods that allow you to get the answer without having a long derivation of the whole thing. So it's interesting that something very special happens for the circle, that you have to have a very specialized type of argument for and only the circle, and then everything else, there's like a easier way to compute the fundamental groups of other spaces. So it's just interesting that it works out like that. So let's say what the main theorem is. It's like the main theorem. So the main theorem is, let f be the following path. This is going to be a loop in the punctured plane, defined by the formula that f of t is e to the 2 pi I t. So this is the loop that begins and ends at 1, because f of 0 is 1 and f of 1 is 1. So it's a closed loop that begins and ends at 1, and it goes one time around the circle counterclockwise. So then the fundamental group of the punctured plane at 1, when you write it out, this is what it will consist of. It will consist of the identity. This is the identity of the identity class. This is the homotopy class of closed loops that stay constant at 1. Okay. Then it will consist of the homotopy class of this one. It will consist of the homotopy class of this one, f squared. So f squared, just to recall what that means you do f star f. The way you multiply classes is with juxtaposition. So this is just a loop. So this is just a loop that stays at a single point. This is the one that goes around one time around the circle, right? This is just a single loop. Juxtaposition, you go around one and you follow it through. So you're kind of going around like really twice, but I mean, the problem would be is, you cannot really see the two loops because one goes on top of the other. So maybe I'll draw it like this, but really both of them are on top of each other. I drew it in the wrong orientation, yeah, like this. Then you would have f cubed, which is juxtaposition 3 times. And if you want to see what this looks like as a loop, this one sort of goes around 3 times. Again, we're just drawing separations in the loops, so you get to see them being separated, so it's easier to see. But really, they're all on top of each other because this will stay on the unit circle. So you have all of these, and then you have the inverses, f negative 1. So f negative 1, to remind you what that means, this is the reverse path. So the inverse of a class is the reverse path. So you change the orientation, and here you would go like this. And then you would have f negative 2. This one will go around like this, and so on. So basically, as you can see, the fundamental group is described by the integers. 0 times, this is sort of like 0, 1, 2, 3, negative 1, negative 2, negative 3, and so on. So that's the fundamental group, and thus the fundamental group of this space is isomorphic to the group of integers. This is the integer group. So this is the main theorem. This is the fundamental group of the punctured plane, but it's also the fundamental group of the circle, because the circle has the same homotopy type as the punctured plane, something that we've mentioned last time. Now, we're going to discuss the proof of this. So the issue is that Moncrieff, I'm not a fan of his proof. Moncrieff seems to have an overly complicated proof. What Moncrieff does, so I'll basically tell you what Moncrieff does. So what Moncrieff develops something called covering spaces, and then uses them to find the fundamental group of the circle. That's what Moncrieff does. But this is overdoing it. Covering spaces is completely overdoing it. You're trying to prove something for the circle, and you have to invent a whole new theory out there called the theory of covering spaces just to do that. That's actually an entire chapter in the book. He has an entire chapter dedicated to covering spaces, and he defines what they are, their properties, all of that, and how they can be used to compute fundamental groups. So that's really overdoing it. You're only interested in the circle. It's not really justified to create a whole new theory just to find the fundamental group of a circle. It's an important chapter, but it really should not be done for just a circle. If you're wondering what a covering space is, basically, if you look at a circle and you look at a line, they seem to be almost similar to each other. They're not homeomorphic, but they seem to be very close to each other, because if you pick a point on the circle and you look at it locally, it looks like it's a line. So these two spaces seem very, very similar to each other. Now, the line, the fundamental group of a line is trivial, whereas the fundamental group of a circle is not. And so you're using a line for which you understand the fundamental group to help you determine the fundamental group of this. That's basically what a covering space is. The idea of a covering space is you have two spaces that are very similar to each other. They're not homeomorphic, of course. This is compact, that is not compact. So they're not homeomorphic, but they're very similar. Like locally, if you look at what's happening locally, this does resemble the line. And the idea of a covering space is to replace the original space by something simpler. Simpler in the sense that it has simpler homotopy. The homotopy is a lot simpler to understand. And then you use that other space to help you solve and find the fundamental group of the space you're interested in. That's basically what a covering space is, and you can develop an entire theory of covering spaces. I think that's more appropriate for topology part 2. That is, I would say, a bit closer to algebraic topology, because in order to classify covering spaces, something that Moncrieff talks about, you have to know something about the fundamental group, then you need to know something about cosets and normal subgroups and things like that. So you need to know more algebra in order to understand that kind of discussion. So that's why I think it's more appropriate for an algebraic topology course. I think that should be more appropriately done in a topology part 2 class. So like if I was teaching topology part 2, I would put that into the second continuation class. I think that in order to find the fundamental group of a circle, you need to have a more specialized argument just for that, just for the circle. So that's what we're going to discuss. So I'm going to give you the idea. So what we're going to do is I'm going to give you the idea. So we will describe the idea and then make it rigorous. And I would say that in a way, what Moncrieff does in his book is exactly this idea, but he never explicitly mentions it. And a lot of the intuition is therefore lost in his discussion. So here's the idea. So the idea is that given a loop that, let's say, starts and ends at some point, let's say 1, we can find the winding number. So let's say the name of the loop is f. We can find the winding number of f, which says how many times f winds around the origin. So that's what you call the winding number. If you've taken a class in complex analysis, maybe you've seen this before. How many times something winds around the origin. So let's just draw some pictures. So let's say this is the origin, and then we have something that goes like this. This is f. The winding number in this case, the winding number of f, is going to be 0. Because 0 is outside, the origin is outside this path, closed path. So it does not wind around the origin. It never encloses it. So here it would be 0. Now, if instead, let's say the winding number does this, then in this case, well, it's going to depend on the orientation. So if we go, let's say, counterclockwise, this is what we call the positive orientation. So here, if it goes like this, then the winding number is going to be 1. It winds one time, it revolves one time around the origin. Now, it's true that you have these loops over here, but these loops do not go around the origin. Okay, so that's what you have to be careful. These loops are not going around the origin. So we have this. Okay, and let's change the picture. Let's say we had something that goes, let's say, like this. Actually, let's say it goes clockwise, and then it goes clockwise like that. Okay, so we go round, and then we go round. Then here, and this is the origin, let's say, then the winding number of f around the origin would be +2. I'm sorry, it would be -2. Yeah, it would be -2, because clockwise in mathematics usually means negative orientation. So here you go, the negative orientation twice around. You see, it spins twice around the origin, so it's -2. And I guess I should say another thing. I should say that if you have this, let's say it goes around like that, right? So it goes around like that, and then you kind of backtrack. So this is the way the path goes. You go clockwise, you go once around, and then you backtrack in the opposite direction. Then here the winding number would actually be 0. Now, if you find it confusing, and you can say, but you're going twice, that's true, you are going twice around it, but think about, so this is how you want to think of it. Imagine you are standing at the origin and looking at the curve. How much do you rotate your head? So here, as you're spinning around, you have to spin your head around one time and then a second time as you travel around this curve. So then you would see it spin 2 times around in the negative direction. So that's -2. Here, you will spin your head one time around, but then you unspin your head one time around. And so the net change of rotation in your head that occurs would be 0. So that's what we call the winding number. And that's the basic idea of a winding number. And so there is a trick. So let me just say this. There is an easy way to find the winding number visually from a picture. So let's say we have a very complicated, so that was not very complicated looking curve like this. Okay, and let's say it moves like this. It moves like this. So let's just add some arrows so we see the orientation. Like this. Okay, so here's a very complicated curve. right? Very complicated curve. And then we're going to draw the center somewhere. So let's say right over here. Yeah, let's put it right there. Maybe we should even zoom in a little bit. And then I ask you to find the winding number of this loop around the origin. Well, that's kind of confusing to find. I mean, you can maybe carefully figure it out, but I'm going to show you a fairly easy way how to do it. So this is basically what you need to know. So it basically just comes down to this. If you have, so if this is the origin, so let's say this is the origin, and then you have a circle going clockwise, counterclockwise, and you draw this ray, this is a ray escaping out to infinity, so this is a ray that escapes out to infinity, then if you cross, so if the curve crosses, so if the curve crosses the ray from right to left, then it's going to be +1, right? So you see, you make this ray come out, and the curve, because of the orientation, it's crossing from the right side to the left side. That's how it crosses, +1. However, if this is the origin, and let's say the circle goes like that, and you draw your ray escaping out to infinity, now you're crossing from left to right. So from left to right, you're going to write down -1. And that is the way you figure out what the winding number is. So it's the same idea, just in a more complicated picture. So here what you do is you draw a ray escaping out to infinity. Now, it does not matter how you do it. This is probably the easiest way to do it. But the one thing you do not want to do is you do not want your ray to pass through a point of intersection. Then you do not know which one it is. It's kind of like both. But you can make it, it does not even have to be a straight line. It can go like this. It can go like that. So let me just show you. So let's say you draw a line, a curved line, escaping out like this. Then you're just going to find all of the places where you have an intersection. So you have an intersection over here, an intersection over here, an intersection over here, and an intersection over here. So you just find what those intersections are. This one is going, the orientation goes from left to right. So if it's from left to right, it's -1. This one is going from left to right. That's -1. This one is going from left to right. So that's -1 also. What about this one? This one is going from, so you're kind of pointed this way, and then you're going from right to left, right? It's pointed. Oh, sorry, I already made a mistake. Sorry about that. So let me start again. I think I made a mistake already. So you see, the ray is going in that, so you're pointing in that direction. You're moving from the left to the right. So this is -1. Here, you're pointing towards that direction. That's the direction of the ray. And you're moving from left to right. So from left to right, that's -1. Here, the ray is pointing that direction, but now you're going from right to left, from right to left. So that would be +1 here on that intersection. And here, you're pointing in that direction, and you're moving, the orientation of the curve goes from right to left. So that's +1. And so the winding number around that point is therefore going to be, you add up the numbers, it's going to be 0. So the winding number is 0. What if we tried something else? So usually you try to find this easiest possible ray, like this. That's the easiest, but the least number of intersections. So now you can see, because of the orientation, you're going from left to right. So you're going from left to right. So from left to right, this is -1. So this one is going to be -1. But this one is going from right to left. That's +1. So -1 and +1, that's going to be 0. Okay, so that's kind of the way you can figure it out. So there the winding number is going to be, so the winding number at that point, at the origin, is going to be 0. Okay, so if you pick a different point, let's just do one more. Let's say we use this one right here. Let's say that was the origin. That was the origin. Now the easiest way is, of course, is to go like this. Then what is the winding number? Well, here we're going from left to right, and here we're going from left to right. So from left to right, it would be -2. So at the winding number around the origin, if that was the origin, is -2. But we can also do it the more complicated way by just going like this. And then here we're going from left to right. So that would be -1. This would be -1. This would be +1. This would be -1. This is from right to left. This would be +1. And that would be -1. So we add up the numbers, -1, +1, -1, +1. They cancel away, and then you have -2. So you end up getting the same answer. So that is the quick visual way you can get the winding number. Of course, we cannot prove this, what I just did, because it's visual. You do not, like, formal mathematics is not visual, but it's nice to have these pictures in mind. So that's what you call the winding number. And here's the interesting thing about the winding number. So if F and G are homotopic, F and G are homotopic loops in the punctured plane, if and only if the winding number of F is equal to the winding number of G. So that is the surprising result. So two loops are homotopic if and only if they have the same winding number. And we're going to prove it. And then from here, the theorem follows. The theorem will follow immediately, because now you can define your... So if you're willing to accept that, two loops are in the same homotopy class, if and only if they have the same winding number, then you have the following isomorphism. So then we can use the winding number to construct an isomorphism between the fundamental group of the punctured plane and the integers. So what's the isomorphism? So let's call this isomorphism wind, because it comes from the winding number, and it's a mapping that takes you from the fundamental group of the punctured plane, and it maps you to the integers. And the mapping here is this, that the winding number of a loop, so a homotopy class of a loop, is just equal to the winding number of that loop. Now, this is well defined, because if F and G are homotopic, so if you have a different representative for the same loop, then the winding numbers become the same. They become the same. So this is well defined, right? This is a well-defined mapping. There is no ambiguity. You always get the same answer, regardless of what class you pick in your, well, whatever loop you pick in your homotopy class. It will always come out to be the same thing. Furthermore, this mapping is injective. It's injective because of the other condition. If two loops have the same winding number, then they must be homotopic. So in other words, if you have two homotopy classes that map to the same integer, then the two homotopy classes must be homotopic to each other, and so they must be in the same class. So that's why the mapping is injective. It maps a unique homotopy class to an integer. There's only one. So the map is injective. Why is the mapping surjective? And then finally, why is the mapping surjective? Well, that's very simple. Mapping is surjective because if f of t is defined to be this, so if this is the loop that we talked about before, this is the loop that goes around one time around the origin, then the winding number of this loop is +1. And so the winding number, if you do it 2 times, if you juxtapose and you just go 2 times around, then that would be +2. And if you do the winding number of f star f star f, that would be +3, and so on. And then you can use the reverse. The winding number of the reverse path would be -1, and so on. So this way you can get all of the integers. So that's why it's surjective. You get all of the integers. So it's surjective, so you get every integer. Finally, we have to check if it's a, so, and then finally, this mapping is a homomorphism of groups for a very simple reason. Because if you want to find the winding number of F multiplied by G, that would be equal to the wind of F juxtapose G, which would be the wind of, so you get rid of the homotopy class, you just look at a single representative, and the winding number of a juxtaposition is the winding number of F plus the winding number of G, because you first go by F, that gives you some winding number, then you go by G, that gives you an additional winding number, and it's just the sum of whatever those two are, and that is a group. You see, that's a group isomorphism, because when you show that something is a group homomorphism, you take two elements in the group, you multiply them together, and you show that they get mapped to the binary operation in the other group, right? So you can see these two wind. So like, think of it like this: F plus G is F plus G, right? Basically, so it's a group homomorphism. So this is a group homomorphism. It's injective, it's surjective, so it's an isomorphism of groups. And we have just justified why the fundamental group of the punctured plane is isomorphic to the group of integers. So that's the justification. That's really the main idea. It's a very nice idea. It's a very elegant kind of derivation. The one issue is, and this is really what the issue is how does one define the winding number in a rigorous manner and then justify those properties? So this is fine, assuming you can justify those kinds of properties. So that's what we're going to do. We're going to discuss how you can define the winding number rigorously, and then we can show what those properties are. We can justify those properties. So let's remove this. And what I'm going to do is I'm actually going to use, so this is based on a book by Lars Alfors. And the name of this book is called Riemann Surfaces. Lars Alfors, I'm sure perhaps many of you heard of him. He was a mathematician. He's not alive anymore. He was a mathematician who worked in complex analysis. And I think he written two books. Maybe there's other books, but there's two books. One of them is a book on complex analysis. I think the name of the book is called Complex Variables. And the other book is Riemann Surfaces. And a Riemann surface, if you're wondering, it's a generalization of complex analysis. Complex analysis takes place in the complex plane, but it is possible to generalize complex analysis on a more general type of an object called a Riemann surface. And that's what Riemann surfaces are. And Lars Alfors was a leading mathematician in the subject of complex analysis and Riemann surfaces. So there's a book that was written by him on Riemann surfaces quite a while ago, maybe 60 years ago or something like that, if not more. And I was able to find his exposition on this. It's not an easy book to read. It's very dense. There's no motivation. There's no pictures. There's not a single picture in the whole book. And the arguments are very dense. And he's not really telling you what the idea is. He just shows you the proof. So I looked through the topology section of the book, and he does talk about winding numbers in the book. And I thought his treatment was actually pretty good because it's a fully rigorously written book. And his explanation is pretty short. So it's applicable for what we're going to be doing. I'm going to try to give you some intuition for what we're about to do, and then we'll make it more rigorous afterwards. If you've had older professors, maybe if you had professors in their 70s or something, and you ask them for a book recommendation on complex analysis, they'll probably mention Lars Alfors and his book on complex analysis, though I'm not sure. I've never read his book on complex analysis, and I'm not sure if it's the best book on complex analysis. It's just that 60-something years ago, there were a lack of books, and that was like the go-to book people would look at if they wanted to learn the subject. Nowadays, there's a lot of books. There's even books written for undergraduates. So maybe those books they presented in the more comprehensible kind of a way. I've never read his book on complex analysis, so I cannot really comment on that. But it's just that a lot of the books in the math world, like for example, Complex Analysis by Lars Alfors, one of the reasons why they become classics is because they do not have many competitors. So those are like the standard books that people use. I would use the same analogy with Rudin. the book Principles of Mathematical Analysis. That is a classic. That's another classic in math. But it's not, I would not say it's the best book to learn analysis from. It is very dense. And there's, over the years, people have written books that are more motivating for things for ideas and analysis, but that just became sort of the standard text on real analysis when there were a lack of books. So a lot of people learned real analysis from that book. So if you ask perhaps some of your older professors in their 70s or 80s for a book on real analysis, they probably might say the book by Rudin, because that is perhaps where they first learned it from. But nowadays, I would argue there's better books on mathematical analysis if you're trying to get into it. So it's nice that we have classical books, but people have found a way to improve upon them. So I just bring it up because Lars Alfors was, top leading mathematician in complex analysis, and sometimes when you're interested to learn something, going and reading the book of the top mathematician on that particular area of math that they've made a lot of progress in is not always necessarily the best book to use. There might be better books out there, but I'm not really in a position to comment because I never really read the book. So I'm just going off by what other people have said. Some people have tried to work through the book and they said there's better books out there. So just based on what I heard from other people. But anyway, there's this book, Riemann Surfaces, and I'm going to show you how Lars Alfors defines the winding number in that book. So here's the way he does it, but here's some motivation for how this works. So let's assume, so for simplicity, let's assume that we have a function. So this is going to be a closed loop into a circle. And f of 0 and f of 1, they will be the same point and they will be 1. Instead of the punctured plane, let's just work on a circle. It's just going to make everything a lot easier. Yeah, so perhaps I should just begin with the punctured plane and then show you how you can reduce it to a circle. If in general, if you have something in the punctured plane, like this, let's say, this is f. Then f of t, this is a point in the complex plane. And since it's a point in the complex plane, you can write it using Euler's formula. It has a radius and it has an angle. Now, the radius and the angle will depend on t, right? Because as you move along, whatever the radius and the angle is here would be different from the radius and what the angle is there. So the radius of that complex point and the angle that it creates will vary depending on time. So really, this is r of t, and this is theta of t. So you're saying that you can express your function in this kind of form, r of t e to the I theta t. Now, r of t, that's sort of easy to find. R of t, that's just going to be the norm, the absolute value of this. So r of t is actually very easy to find. R of t is just going to be f of t, the absolute value of f of t. A complex number has, you can always calculate the absolute value of the complex number, which is just the distance from the origin, and r of t is just whatever that is. And you should notice that if f of t is a continuous function, which we're always assuming is the case, if this is a continuous function, and when you take its absolute value, that's also going to be a continuous function. So this is a continuous function. Now, the angle is actually where the complication arises. So the entire complication arises when you have an angle. Because, so the angle is what causes all confusion. Because the angle is not unique. You can define the same angle in many different ways. So for example, here we have a point. What's the angle over here? Now let's say it's pi over 6, right? 30 degrees. You say it's pi over 6. But you can also say, right? You can also say the angle, so you can say the angle is pi over 6. You can also say, you can add 2 pi to that. So you can say it's pi over 6 plus 2 pi. Or you can subtract, you can actually subtract 2 pi twice. So there you can subtract off 4 pi. So you can do all of this. All of these will be valid choices for the angle. And the question is, which angle should you pick? Now, you might say at first, does it really matter? And it actually does if you want the function to be continuous. If you want this function to be continuous, then it does. So let me show you what happens as we travel around the circle and what kind of problems arise with the angle. So let's say we start right over here. Okay, we start our path at that point, and we're going around like this, counterclockwise. So we move over here. Now, when we're up here, there's not really much confusion. The angle is 0. So we would say this angle is 0. We would say this angle is, let's say, pi over 6. This angle is pi over 3, let's say. Let's say this is pi over 2, pi over 2. And you keep on drawing these angles. Maybe this angle right here is 3 pi over 2. And then you have an angle there. You have an angle here. But, yeah, so you keep on drawing these angles, right? You keep on drawing these angles, all of these angles, I guess. And maybe I should change the picture a little bit to show you the point that I'm trying to make. So let's say we go around like this, okay? So I think this picture will better explain what's going on. So the angle here is 0, pi over 3, pi over 6. There's a certain angle. And now as you come around back, what would be the angle at that point as you come around back to it all over again? So you could say the angle is 0, but you could also say the angle is 2 pi. You see, as you come around back. The problem with making the angle equal to 0 when you return back to the point is then you have a discontinuity. The theta function kept on increasing at a steady pace, and then suddenly it just jumps to 0. And then you have a discontinuity, and then this function is not going to be continuous. And then what do you do after you complete the loop? So this, after you come back, as you go around and you come back to where you started, you would say that the angle should be chosen to be pi over 2. But then when you start going along the second loop, you see, you're going along the second loop. How should you now define the function, this theta of t function, as you go around the second loop? The problem with making it equal to 0 is then you again have a discontinuity because it's supposed to be equal to 2 pi. So on this point, let's say, that point, you might want to make the angle, let's say, pi over 6, but you cannot make it pi over 6 because then you're introducing a discontinuity. It's currently at 2 pi. So really, the angle should be chosen to be pi over 6 plus 2 pi. And that's where the difficulty comes from. The angle is not unique, and there's lots of ways to assign the angle. And the point is that the idea is you can write the function in this form, and then this is going to tell you what the winding number is. So then the winding number is going to be calculated like this. Theta of 0, this is the initial angle, which in our case, that's just going to be 0 because we're starting at 1. That's the initial angle is going to be 0. And theta of 1, this is the final angle. This is the final angle, this is the terminal angle, after you do the full revolution, whatever that is. And so in the picture that we just drew, where you go around like this, theta of 1 is going to be 4 pi. It's going to be 2 pi and then another 2 pi, because it has to be continued in a it has to be continued beyond that point to vary in a continuous manner. So it has to be therefore be chosen to be 4 pi. Okay, so in this particular case, it's going to be 4 pi. And then the way you then find the winding number of around your loop is you're going to take theta of 1 minus theta of 0. So this is the total change in the angle that occurs. So it's the angle that you start at. In this case, it's 0. Theta of 1, that's the angle that you finish at. And this is some multiple of 2 pi, right? So if you do theta of 1 minus theta of 0, that's going to be some multiple of 2 pi. So it's going to be 2 pi, and then it's going to be some integer multiple, some integer. And whatever that integer multiple is, that is the winding number. The winding number is just the integer multiple. So it's 2 pi times whatever integer that is. So in this particular picture, because as you can see in this picture, it's going to be 4 pi, the integer multiple is 2. And so the winding number in this particular case around the origin is therefore going to be equal to 2. Okay, so it's the change in the angle that occurs. That's basically the way the winding number is calculated. But there's a difficulty is how do you make this work out? Now, for simplicity, we said imagine that you're on the unit circle. So if you're on the unit circle, then there is no R of t. R of t is just 1. So it really makes it work, and you can just focus on the angle itself. Now, when you're located on the unit circle, the situation is still complicated, because when you're on the unit circle, paths can still be very complicated. So you might think everything's simple because you're on the circle, but that's not true. So here's a circle, and here's an example of a path. Let's use this thick color over here. You might go like this, okay, and then you kind of go back. Then you go forward, you go back, you go forward a lot, you go back. So you see, you kind of can move like this. Nobody is saying you have to move in some kind of nice, reasonable way around the circle, right? No one is saying that. Or maybe, yeah, maybe, so maybe if I draw it like this, it will make more sense. You kind of go like this, just to show the exaggerations or something. Like you can be moving along the circle or maybe just all the way around until you return back to where you are. So, and then this is your circle. And now if you just sort of map everything back to the circle, this is the kind of picture you have. Now, of course, when you kind of collapse it back down to the circle, all of this kind of goes on top of each other and it's hidden in the circle. So you do not see all of those complex motions, back and forth motions. You do not see them. But in general, a closed mapping can move like it. Nobody is saying it has to nicely vary around the circle at constant speed. It could certainly be a lot more complicated than that. And that's actually the reason why previously we drew pictures in the punctured plane, because you can just make that idea a little bit more explicit with the pictures. So anyway, so that is what this is. And what we want to do is we will define the winding number of F, the winding number. So here's the way you do it. So this is the way Alfors does it. So what you do is you're going to partition the unit interval into smaller subintervals. So let's call this T0, T1, T1, T2, let's say Tn minus 1, Tn, like this. You partition it into smaller subintervals. So the picture is, so here's 0 and 1, and then you cut it up into smaller subintervals. Now, the subintervals, they do not have to be equally spaced, but you could make them equally spaced if you wanted to. So you partition it into smaller. Now, it's not a true partition because there is an overlap at the point, but let's not worry about it. So you break it up into these subintervals with the requirement so that if, let's say, Z and Z prime, so these are two complex, I'm sorry, that makes no sense. If T and T prime belong to the kth subinterval. Now, this is funny. Alfors uses the I notation. And that's funny because you're doing complex analysis, but I represents an index and not the complex number. So maybe to avoid confusion, let me write it as Tj minus 1 Tj. Okay, so if you pick two moments in time in the jth subinterval, then f of t prime minus f of t will stay bounded by 1. It will stay bounded by the number 1. So this is possible. This is possible because of something called uniform continuity. So this is not, you learned this in an analysis class, in an advanced calculus class. And maybe this will make a good exercise on the homework to explain why you can do it. But let me perhaps show you a picture for what's going on. The picture will help clarify. Here's our circle, okay? F of t, that's some point on the circle, right? Because this is a closed loop in the circle, so it moves around the circle. So f of t is something on the circle. So this is f of t, and f of t prime might be over here. And f of t, so f of t prime minus f of t, that's going to be the distance between them, right? You just draw the line and you find the distance between them. Now, the very maximum that this can ever reach is when these are on opposite sides of the circle. So the maximum this can ever reach is 2. Okay? And uniform continuity says that if you make these intervals small enough, then no matter which subinterval you locate it, if you take 2 time increments in every subinterval, if you take 2 of them, they stay reasonably close together. So you do not end up in a situation where f of t prime is over here and f of t is like on the near opposite side of the circle. In other words, they're getting too far apart from each other. Too far apart. So they stay reasonably close together. So reasonably close here is the distance between them is bounded by 1. Okay? The reason why we want to do this is because that's the way we're going to find the winding number. Like basically the idea of how you find the winding number is you have you basically take a point and you take a nearby point, and then you see by how much the angle changes, like local change in the angle. Because if they're really far apart, like if you have all, like let's say you have, yeah, so let's say you have something really, really complicated like this, and this is one point, and this is the other point. Well, by how much does the angle change? It's unclear because you're moving around quite a lot. So the idea is you can talk about how much the angle changes locally. You can, if you have this point and you have this point and they're right next to each other and they're not too far apart, then you can talk about how much the angle changes by. So you kind of keep them somewhat close together. So you do this. And then the next thing that you do is you can choose. So then you're going to choose. So then if you do f of tj divided by f of tj minus 1, that's going to be equal to e to the I theta j for some angle. For some angle theta j that's smaller than pi over 2. So let me explain what just happened, because this is somewhat confusing. So if you look at Alfors's treatment of it, he sort of just asserts it. And this is a little bit confusing, but let me explain what's going on. You need to understand that f of t and f of t prime, there are points on the circle. So if you have a point on the circle, if you have 2 points on the circle, so let's call this z and z prime. You can write them in Euler's notation. This would be like e to the I, let's say alpha, and this would be e to the I beta. So this is the way you would express 2 points on the circle using Euler's formula. Now, if you want to find the angle that changes between them, the way you can do this is you can divide the two complex numbers. So if you do z prime divided by z, this would be e to the I beta divided by e to the I alpha. And by subtracting them, by dividing the exponentials, you would have e to the I beta minus alpha. So beta minus alpha, it's the change in the angle that occurs between them. Okay, that's the basic idea, that if you want to determine how much you have to rotate between two complex numbers on the circle, you divide them and then you find the angle. And this is what Alfors says, that you're going to, so you create the partition, right? You take the partition, you break up the partition, and then you look at all of the points. So you take two adjacent points in the partition and you divide them. Now these are points on the unit circle, so they will all have the form e to the I theta. And he's claiming that you can choose this angle to always be smaller than pi over 2. That's what he says. You can always make it be smaller than pi over 2. The question is, why can you do this? So the reason why you can do this, so I'll give you the geometric explanation, and then I'll give you perhaps a rigorous explanation, like a more algebraic explanation if you do not like the geometry. But what you're doing is, if you take 2 points in the partition, so these are like the partition points, if they're adjacent to each other, they're in that interval, and they satisfy this inequality. So the picture here is wherever t, so if this is f of tj minus 1, wherever tj is, it cannot be too far away. It has to be less than or equal to 1. The problem would be if they're on the opposite side. You see, if they're on the opposite side of the circle, the distance reaches 2. And when the distance reaches 2, the angle of moving from that one to that one goes from, it's like 180 degrees. It's either 180 degrees like this, or it's 180 degrees like that. So by making sure that it's less than or equal to 1, you can ensure that the rotation that you have to move, so you're either moving clockwise or counterclockwise, the rotation that you have to move will stay under 180 degrees. So that's why it's between negative 90 up to 90, but not including 90. I mean, it's because of that inequality, right? So that's the way you can do it. You can find some number, right? Some unique number. In fact, it's a unique number, right? There's some unique theta that will satisfy that. Okay, that's kind of like the geometry of why you're allowed to do that. Now, so to justify this, right? So to justify this, this choice of theta j, note that if you let w represent that ratio, actually let's call it z for complex number. If z represents that ratio, then z minus 1 is less than or equal to 1. Why? Well, just open up the inequality. So what is z? It's f of tj over f of tj minus 1, which, so this is z minus 1, right? Z minus 1. So z is this ratio. And if you do the fractions, this would be f of tj minus f of tj minus 1 divided by f of tj minus 1. But what do we know about adjacent points in the partition? They're bounded by 1. So this is bounded by 1, and the denominator, well, that's a point on the unit circle, so that's 1. So you have this inequality, that z minus 1, whatever that ratio is, z minus 1 is less than or equal to 1. And what region is this? What region? Well, this is a complex number. This is the equation of a disk, which is centered at 1 with radius 1. So you have 1, so it's this. So z, wherever z is located, it has to be located somewhere in the disk. And so the real part of z must be positive. It must be a positive number. So if the real part of z is a positive number, then it means that z is in the right-hand plane. And if you're in the right-hand plane, you can either, the angle goes up to pi over 2, and in the opposite direction, it either goes down to negative pi over 2. So that's the reason why you can do this. So you can express this ratio like this. So that's kind of like the justification for why you can do that. But I'm going to take this down. This is kind of a distraction. I think all of this is a distraction. That's not the main idea. So the main idea is these ratios, they tell you the angle by which you're changing by, and you're going to call that angle theta j. And here's how you define the winding number. And then we define, so then, what happens if we add up all of the angles? So the sum of all of these angles, theta j. There's going to be n angles because there's n intervals on which we're doing this. We're doing this for each of the subintervals. So for each of the subintervals, we're doing this, and we're calculating this theta j. So if we go ahead and we compute this, then what do we get? Then we get that the sum of theta j is equal to 2 pi times some integer. So the sum of the angles must be a multiple of 2 pi. So let's just justify that. So here's justification. So if that's not clear, here's a justification. Basically, let's take I theta 1, EI theta 2, EI theta 3, and multiply them together, EI theta n. So let's multiply all of these complex exponentials. That's what we have. Now, each of these complex exponentials are given by these ratios. So this is f of t1 divided by f of t0. This is f of t2 divided by f of t1, all the way up to f of tn divided by f of tn minus 1. Now, on the right side, this is a telescoping product. This cancels with this cancels with this cancels with that. And in the end, you're just left with 1. Because f of tn, that's the endpoint of the interval, that's f of 1, that's 1, and f of t0 is also 1, because the path begins and ends at 1. So that's just equal to 1. But what is this? This is e to the I, and then it's the sum of the angles. The sum of the angles. So the sum of the angles is equal to 1. So e to the I of a bunch of angles is 1. So by Euler's identity, if e to the I of an angle is equal to 1, then it means that the sum of these has to be a multiple. It has to be a multiple of, like by Euler's identity, what is this? This is cosine of the sum plus I sine of the sum is equal to 1. So when does that happen? That happens when the sum of the angles is 2 pi, right? Sine of 2 pi is 1, and cosine of an angle is 1 when it's a multiple of 2 pi. So the sum of the angles has to be equal to 2 pi. It has to be a multiple of 2 pi times some integer. Has to be equal to 2 pi some integer. And whatever integer this is what we call the winding number. So the winding number is whatever integer that is. So if you want to say what the winding number is, you can say that the winding number of f is equal to 1 over 2 pi times the sum all of these angles that you get when you introduce the partition. So that's the definition of the winding number. You're calculating the total net change that occurs in the angle when the angle moves through a continuous process. So that's the way you can define the winding number. Now, there is an issue here that you perhaps noticed with this definition. And in this definition, you're choosing a partition. You're choosing a way to subdivide the interval. So because of this, you can be skeptical and you can say, well, how do you know the answer comes out to be the same thing? Maybe if you had a different partition, maybe if you cut it up differently and you recalculated these angles, you would get something different. So we've cut it up into, let's say, n subintervals. So let's say we have 20 subintervals. But what if we use 600 subintervals? Would we get the same answer? And it turns out you do get the same answer. And this is going to be an exercise I will put for you on the homework exercise to show that this definition does not depend on the partition. So even though you're making a choice of a partition to calculate it, in the end, all calculations will lead to the same answer. So that is going to be on your homework. Now, the next thing that I would like to show you is that the winding number does not change under homotopy. So that's the next thing I want to show you. So let's discuss this, that if f and g are closed loops in S1, f of 0 is equal to g of 0 is equal to f of 1 is equal to g of 1 is equal to 1. So these are closed loops. So if f is homotopic with g, then the winding number of f would be equal to the winding number of g. And so the winding number only depends on the homotopy class. So that's what we're going to show next. So here's how we do it. So if we have two paths and they're homotopic, so I'm going to take this down because that's we want to show the winding numbers are the same. So we have to go back to the definition of what a homotopy is, that they're homotopic. So if they're homotopic, then there is an H. There is an H, a homotopy mapping from I times I into S1. So let's think of the first one as representing time and the second one representing interpolation. And the following properties would be satisfied. That H of 0s would always be 1. H of 1s would always be 1 because those are the endpoints. The endpoints never move in a path homotopy. So to quickly remind you, this is like the difference between a path homotopy and a homotopy. A homotopy of continuous maps is just a continuous interpolation. There's nothing about endpoints. In a path homotopy, it's a continuous interpolation with the added requirement that the points stay unmoved throughout the interpolation. So this is a path homotopy. And then you would also say H of t comma 0 is the function f of t, and this would be H of t comma 1 would be the other function g of t. Okay, and the next thing that we're going to do is, so here's the picture of our, so we have a mapping. So this is I times I. So this is our unit square. And we're going to partition the unit square into smaller pieces. We're going to cut it up into smaller pieces. You can assume that these are equal subdivisions. It really does not matter. You can, if they're small enough, you can make them all be the same size. So we're going to partition 0, 1. So this is the t-axis into subintervals. Let's say t0, t1, t1, t2, Tn minus 1 Tn. And you're also going to partition it. So you're going to partition it horizontally and you're going to partition it vertically. And you can do this because of uniform continuity. It's the same reason as before. You can make them small enough. And then you do S0, S1, S1, S2, Sn minus 1, Sn. So you break them up apart like this so that what happens? So that if you have 2 points, so I'm just going to call these points, for lack of a better name. Well, let me say it like this. If you have T, if you, let's say, have T comma S and T prime comma S prime belonging to one of these. So this is like one of these subintervals. So that would be, let's say, belonging to Tk minus 1 Tk. I guess maybe I should call this Tj. Tj minus 1 Tj times Sk minus 1 Sk, like this. So if both of them belong to that subinterval, if they're both sufficiently close together, so then F, so not F, H, because H is the homotopy, then H of Ts minus H of T prime S prime would be sufficiently close to each other. So it will be within 1. Very similar to what we did before. It's the same idea. The main idea what this is based on is that this is compact. The reason why you can subdivide the interval that we've said in the previously when we talked about the winding number and how you can cut up the interval in that way, that is mainly compactness. That's what it has to do with. Compactness is the main idea. So this is compact also, so you can subdivide it in this sort of a way. Okay? And so what happens? So here's the idea. So let's say what the idea is. Now, to fill in this picture, I think this will help you see what's going on. This bottom row of the square is supposed to represent f. Because how do you get the bottom row of the square? You set s, which is the vertical axis, you set it equal to 0. So when you set s is equal to 0, you recover f of t. The upper row, the top row, is supposed to represent g. And then everything in between is a continuous interpolation between those two. So that's like everything in between, between those two. So the idea is we're going to take two adjacent rows. So if you take two adjacent rows, so let's say we take, to make the picture perhaps, let's do it like this. Let's take the row that's right above it. So this is the one that's right above this one. But the main idea is you're going to take two adjacent rows. So the idea is to take a row at, let's say, k, at k minus 1, and its adjacent row at k, and argue that those two curves, those two loops, have the same winding number, i.e., so the winding number of ft comma sk minus 1 is equal to the winding number of ft sk. That's what we're arguing. So sk minus 1. So when the s index is equal to k minus 1, we are located on one of these rows. So let's say the blue one right over here. So let's say k is equal to 1, okay? So then we're located at the very beginning. If you set k is equal to 1, you get s0, but s0, that's the beginning of the interval. So you're all the way down here. Then sk would be the one that goes immediately above it. Now notice what we have here. And I made a mistake. I wrote f. I meant to say h, of course. Sorry about that. Because the homotopy is h, so it's h, h, and h. So if you set this to be the initial one, and then you vary t from 0 to 1, that gives you the original loop f. Now, if you set k is equal to 1, and you let t vary from 0 to 1, you get this blue one. But this blue one is being mapped to a loop, right? This is being mapped somewhere in your space. The endpoints of this blue thing, of this blue line, get mapped together to 1. Okay, so this is some path, this is some closed loop, and this is some closed loop. And we're going to argue that these two have the same winding number. And once you can show that these have the same winding number, then this is the way the argument's going to go. This one will have the same winding number as that one, but then the blue one will have the same winding number as the one that's above it, and the one that's above it will have the same winding number as the one that's above it. And as you build on that, you then arrive at the conclusion that the one at the beginning and the one at the end had the same winding numbers throughout the continuous deformation process. So that is basically what we are trying to do. That's the idea. We're basically trying to do all of that. So how do we make this work out? So here is how we do it. So we first have to calculate the winding number for this one. So we begin by calculating this, we calculate this, and then we end up showing why they're the same. So here's how we do it. So we have to go back to the definition of the winding number. So how do we end up calculating the winding number of this? So the way you calculate the winding number of a function is you take your partition. You see, this partition has been created in such a way so that as long as they're all in the same subrectangle, they're all less than or equal to 1. So that condition is satisfied from the earlier definition. So we're going to keep this one fixed, and we're going to let t go through all of those subintervals, and that will calculate for us the angles. So what we do is we do f, not f, h. I keep on writing f. I meant to say h, because we're calculating the winding number of this. So that would be h of tk, comma, let's say sk minus 1 divided by h tk minus 1 comma sk minus 1. So if you find this confusing, just recall how you find the winding number. So recall how this went. You had a partition. How do you find the winding number? You take tk, you divide it by the previous one, you calculate whatever angle that is, and in the end you add up the angles. Right? That's basically the way it works. If you have a closed loop, you partition the interval from 0 to 1, you take the two adjacent ones that are together, you divide them, you find the angle, and then you add up the angles. This is exactly what we're doing, except this sk minus 1 stays fixed, and it's the t that varies from t0 to 2n. So it's exactly what is before, except we have an h over here, and we keep this one fixed. So this is the winding number for this path. So that's what we're doing, and we calculate what these angles are. So this is going to be equal to e to the I theta k, where theta k is something that's less than pi over 2. And then we do the same thing for this one. We do the same thing for this one. So this is going to be h of tk sk divided by h of tk minus 1, I should say, tk minus 1 sk, and that would be equal to e to the I. So we know we can express it as some angle. So let's call that angle phi k. And here phi k is less than pi over 2. Okay, we have this. And we're going to do one more thing. We're going to do one more thing. So let's draw this picture. One more thing. So here's our picture. So let's draw this rectangle. So this rectangle, this point is located at tk minus 1 s. Okay, I see some annoyances. I'm using k and k. I should have used something else. What letters did I use here? So I used a j on the t. So let me be consistent with that. And let's just change this. So let's just change these to j's. Yeah, let's just change these to j's just to be consistent with that. So let's just change all of these. So that would be tj, tj minus 1, tj minus 1, theta j, and phi j. And this would be j, this would be j. Okay, so we have tj minus 1, comma, sk minus 1. This one is going to be tj, sk minus 1. This one is going to be tj minus 1. And then you're going to have sk, and this one is going to be tj, sk. So this is what we have. The most difficult thing here is we're tempted to use the letter I for index because that's usually what we do. At least that's what I do. But I'm deliberately trying to avoid it because we're working with complex numbers, so that looks a little bit funny. Though maybe it's okay. We have this. So what did we calculate? So when we're calculating this ratio, so you see when we're calculating this ratio, what are we using? We're using this one and this one, right? We're using these two. We're finding the ratio of these two. So the ratio of these two, it can be expressed as a complex exponential where the angle is less than pi over 2. And for the other one, we're finding the ratio of these two. As you can see, h of tj sk divided by h of tj minus 1 sk. And we're going to do one more calculation. We're going to calculate it like this. We're going to calculate this one. So we can also do this. We can also say that if you take h of tj comma sk and you divide it by h of tj comma sk minus 1, that is equal to ei of some angle. Let's call that angle CJ. Okay, so call that angle CJ, where CJ is less than pi over 2. Okay, and the reason why this works, it's the same reason why this works. It all has to do with the fact that these are chosen sufficiently close together so that as long as you're within that subrectangle, the distance is always less than or equal to 1. And since the distance is less than or equal to 1, the 2 points on the unit circle, they're not on opposite sides. And so the angle that occurs has to be less than 180 degrees to get from one to the other. So that's why this is doable. So this is the reason why you can do this. So let's find the relationship between these three. So there's a relationship that exists between all of these three angles. So let us find the relationship. Let us find the relationship between theta j, phi j, and psi j. Let's find what this relationship is. So the relationship, it's basically to observe what happens when you take this number and you divide it by this. So notice what happens. If you take this fraction and you divide it by that fraction, you start to have things that look like this. You recover those numbers when you divide them. So let's actually do that. So let's find what that relationship is. So let's take this fraction over here. Okay, that's the fraction, which is h tj sk divided by h tj minus 1 sk. And let's divide it, so this fraction divided by that fraction. So if you divide it, you multiply by the reciprocal, so we're going to multiply this by, flip it over, so that would be h tj minus 1 sk minus 1 divided by h of tj sk minus 1. So we're divided them together. So let me just check that I've done this correctly. So this fraction you just copy and paste it, and this one just gets flipped over. So tj minus 1 sk, and then this is going to be tj sk minus 1. So that's what we have. So you flip it over, and when you divide them, you're dividing this one from this one. So you're dividing the two complex exponentials. So this would be e to the I theta j divided by e to the I. So I meant to say phi j, right? That would be e to the I phi j, and this is I to the theta j. Okay, so now let's, yeah, and this is of course equal to e to the I phi j minus theta j. But let's work this out. You're going to see that this one can be expressed in terms of that one. So I think in order to do that, you have to look at it like this. You have to pair these together, and then you have to pair these together. So if you pair the red ones together, this is exactly that, right? It's exactly that. So if you pair the red ones together, you end up with e to the I phi j. And if you pair the blue ones together, you get exactly the same thing, but instead of j, you have j minus 1, right? That's the change that occurs. So that would be divided by, e to the I theta j minus 1. And all of this is equal to e to the I theta j, phi j goes first, minus theta j, like this. So this implies, let's subtract the exponentials, e to the I phi j, cj minus cj minus 1. I probably mispronounced all of these letters like 500 times at this point, but that's not what matters. I find it very hard to sort of do math, like think math and write math at the same time, and then your hand writes one thing, but you keep on misspeaking and then saying, you see, I kind of did it again. This is phi j minus theta j, like this. Okay, so they're equal to each other. Now, just because complex exponentials are equal does not mean the angles have to be equal. It means the angles have to be equal up to a multiple of 2 pi. So therefore, phi cj minus cj minus 1 is equal to theta is equal to phi j minus theta j plus some multiple of 2 pi. So some integer. How should we call that integer? We have not used the letter m, so let's use the letter m for some integer m. We cannot use n because n was the size of like our partition. That's where the n came from. And here is the main observation. So cj minus 1, phi j, and theta j are all less than pi over 2. Right? They're all less than pi over 2. So what does this mean? If you were to move these over to the other side, and you were to use the triangle inequality, the maximum sum of all 4 of these cannot exceed 4 times pi over 2. So in absolute value, the sum of all 4 of these will be bounded by 2 pi. It cannot be, it has to be strictly smaller than 2 pi in absolute value. So whatever this m is, it has to be 0. Right? It has to be 0. Because otherwise this is impossible. So m has to be equal to 0. Otherwise this is impossible. It's the way the angles were chosen. The angles were chosen to be small. So because all of these are smaller than pi over 2, if you were to put all of these angles on one side and then use the triangle inequality, the maximum you can have will be dominated. You see, it's strictly smaller than pi over 2. It will be dominated by 4 times pi over 2, which is 2 pi. It's dominated by 2 pi. So in absolute value. So this m cannot be 1 or negative 1. That would already be too big. So the m has to be 0. And so the relationship that we get is that cj minus 1 is equal to theta j is equal to phi j minus theta j. That's the relationship. Now we can find the winding number. So here's how you find the winding number. So now let's take the sum of both sides. So if we take the sum on the left, when j goes from 1 to n, of cj minus cj minus 1, that would be equal to the sum, j going from 1 to n, of phi j minus the sum, j going from 1 to n, of theta j. Now this, by definition, that's 2 pi multiplied by the winding number of, so what was this theta j? The theta j represented, you have to kind of go back all the way here, the theta j were the angles chosen when you're on the k minus 1 level. When you're on the k minus 1 level. So that would be the winding number for the closed path in the interpolation that was on the k minus 1 level. And this, the sum of all of those angles, by definition, that would be the winding number of the closed path in the interpolation on the k level. So that would be h t s k minus this. So this minus this, and it turns out this is equal to 0, and therefore the two winding numbers are the same. So why is that equal to 0? This is actually quite simple. This is actually quite simple, because if you write it out, this is a telescoping sum. This would be theta C1 minus C0 plus C2 minus C1 plus Cn minus Cn minus 1. So everything cancels away except the first and last term, and we're left with Cn minus C0. Oh, I made a mistake. C0 does not cancel away. I meant to say C1 cancels away. So it's just the first and last one that remain. So why is this equal to 0? So you just have to return, you have to understand, you have to unravel what this means. The angle at the 0th, so where is it in the picture? So in the picture, where were these C's coming from? They were coming like this, right, when you were moving vertically. So if we return back to our original picture like this, when you're located at the very top, and you're located at the very bottom. So when you're located at the very top, when you're located at the very top and very bottom, you're located at these two functions. But these two functions, they map you to 1, right? They map you to 1. These functions, they map everything down to 1. At the extreme, right? At the extremes, at the endpoints, as you can see, everything's being mapped to 1. And so those are the angles on the point of the unit. This is basically where you start and where you end, right? Where you start and where you end. So these are equal to 0, right? They're equal. These are both equal to 0. So this is just equal to 0. And so this winding number is equal to that winding number. And we have shown what we claimed. Like, what was the idea behind it? The idea behind this was we were to take a row at k minus 1 and the adjacent row and argue that the two loops on those two rows have the same winding number, which then allows us to conclude that the winding number of every loop in every single row is always the same. So this one is equal to this one is equal to that one is equal to that one, and you keep on building it up. And so these two, the F and the G, therefore must have the same winding numbers. So that's the argument. So that's the argument behind that. Okay, so this shows that the winding number is a homotopy invariant. Now, let me give you an exercise for you to do. So here's an exercise that's going to be on the homework. You're going to let F be this mapping, which is equal to e to the 2 pi it, and you're going to show that the winding number of this is equal to 1. And show this by carefully using the definition of the winding number. And you're going to then show that the winding number of F star F, this is when you juxtapose the paths as 2, and then you're going to show that the winding number of F star F star F is equal to 3, and so on. The winding number of F reverse is minus 1, and so forth. That's what you're going to show. So you're basically going to show on the exercise that you can get every single integer by starting with this loop. This loop has winding number equal to 1, and then by doing juxtapositions and reversal of paths, you can get the positive and the negative integer. So you're able to therefore construct every loop of every type of winding number. There's a loop for every, so for every positive and negative integer, you can find the loop whose winding number is equal to that. And you have to do this rigorously by appealing to the definition of the winding number. You cannot just draw a picture, even though intuitively it might be clear. You want to show this rigorous. So what does this mean? So as a consequence, if you're willing to accept this, so what does this mean? So this implies, so as a consequence, this is a corollary. If you were to write out these classes, homotopy class of F to the 0, this just represents the identity. So a class to the 0, that's just notation for the identity. This is the constant path. F1, F squared. F squared just means juxtapose it twice. F cubed. And then you have the negative ones. So negative power means the inverse of that, so that's the reversal path. F negative 2, F negative 3. So a corollary, all of these are different homotopy classes in the fundamental group. They're all different homotopy classes. Okay, so that's a list of them. So it remains to show, right, they're all different. So you've just listed different homotopy classes. So for every integer, you have a different homotopy class. Because their winding numbers are different. If they're different, they cannot possibly be homotopic to each other because the winding number is a homotopy invariant. So it remains to be seen. So to complete our proof, so to complete the proof of our main theorem, it remains to show that if, let's say G, that if G, well, let me say it like, it remains to show that this is the complete list. We're not leaving anything out. This is a complete list of all homotopy classes. So they're all different and there's nothing missing. And then therefore we see it's isomorphic to the integers, homotopy classes. So to complete the proof of our main theorem, it remains to show that this is a complete list of all homotopy classes. So how do we do this? Well, okay, so given a closed loop at 1, we need to show that the homotopy class of G is equal to the homotopy class of F to some power, let's say m. Let's write it like this: for some power m, for some integer m. That's what we have to show. And once we do that, then we win, and the proof is over, and everything is complete. So this part is actually easier. Showing that the winding number is a topological, is a homotopy invariant is actually harder. That's a harder proof. This one's actually easier. So here's how we do this. So let's introduce some notation. So given two angles, so really just two real numbers, let's call them alpha and beta, we define A alpha beta to be the arc path from alpha to beta. Okay, so given two angles, so for example, if you have A 0 pi over 2, what is this supposed to represent? This is supposed to represent the arc path that starts at angle 0, that would be angle 0, this would be angle pi over 2, and it moves like this, okay? Be your path. This is not a closed path, okay? So just make sure this is not a closed path. That's why we call it an arc. It's not a closed path. If you have, however, if you have A pi over 2 comma 0, that would just mean you go from pi over 2 back to 0. So that would just mean the picture would just go in reverse. It would just mean that your path will go clockwise. Also, this very same path can also be denoted, you can also write, this is perfectly fine, you can also write this as A 2 pi, and then you would write 5 pi over 2. That would be the same thing, because 2 pi corresponds to that angle, 5 pi over 2 therefore is that angle, and then you're drawing an arc from there to there. You're drawing it from here to there. Start there and you go there. So that gives you the orientation by which to move. Okay, so this is going to be the arc path. So the A stands for arc, and the alpha and beta tell you the angle at which you start, the angle at which you end, and they do not have to be written in increasing order. If they're written in decreasing order, you just move backwards. That's all what it means. And the angles do not have to be confined to be from 0 to pi over 2. That does not have to happen. Okay, so that's basically what you do. So we're going to introduce this notation. And now I want to therefore show you how the proof is going to go. So this is, I guess you can say this is like a lemma that we're going to use. It's fairly simple. That in a punctured circle, is contractible. So all paths are homotopic to each other. What is a punctured circle? Here's a circle, and you make a puncture, you make a hole in it. Well, if you make a hole in it, you can see that because you have that hole, you can now continuously extend that hole all the way around and contract everything down to a point. So then these will be homotopically equivalent to each other, right? You can kind of imagine opening this up to a straight line, right? It's now homeomorphic to a straight line, and a straight line that's a convex space, and a convex space is, as we said last time, has the same homotopy type as a single point. So if you have a punctured circle, a circle that is missing a point, then all paths are homotopic to each other. So this is the lemma that we're going to use. Okay, so here's what we're going to do. So this is the claim. If G is a closed loop, then G is homotopic. Let's say it like this: the homotopy class of G is equal to f to some power, where f of t is this, it's this loop that's e to the 2 pi it. So it's that loop right there. So that's what we're claiming. We're claiming that every homotopy class is included in the list of classes that we've written out. So that is what remains to be seen. So here's how we're going to prove this. Proof of claim, not proof of lemma. I think the lemma is clear. We talked about that before. So we're going to, again, partition this interval from 0 to 1 into subintervals, say t n minus 1 tn, so that G restricted to, so G restricted to that subinterval tj minus 1 tj omits either +1 or -1. It omits one of those 2 points. Okay, so the picture here is we have our circle, and plus or minus 1, these are the antipodal points that are on the opposite side. The distance between them is exactly 2. So if you make the subinterval small enough, you can make sure that G on that subinterval is always bounded by 1, like what we saw before. So that means you can never run into a situation where G is either here or there at the same time. So this is a subpath. G on the interval from 0 to 1, that's the full path, and that's a subpath. That's a subpath. So the subpath, it might look like this, for example. That's a subpath. It might look like this. Maybe it contains 1. It could contain 1. It could contain -1, but it cannot contain both because it's been cut up small enough not to contain both. Okay, so so what we do next? Now, since G restricted to tj minus 1 tj is a path in the punctured circle. It's the punctured circle because it misses at least 1 point. So if this misses 1, this is therefore a path in the punctured circle. If it misses -1, it's a path in the punctured circle. So it's a path in the punctured circle. So since this is a path in the punctured circle, it is homotopic to an arc. Okay, it is homotopic to an arc. So maybe to make the notation a little bit better to use, whatever that is, G restricted to that subinterval. Yeah, so homotopic to an arc. So let's just say this. So let G subscript j be G of, so we're just going to map tj minus 1 tj. You see, you have this annoying thing that everything has to be rescaled. Like technically, these intervals are not from 0 to 1. So we're just going to take an affine map that rescales tj minus 1 to tj into 0, 1. So that's what G subscript j represents. It's the path So if you, I mean, all what we're saying is you have some kind of path. Like, I'm not drawing it on the circle because I want to make it a little bit easier to see. You have some kind of path. You're breaking the path into smaller paths. So this is like G1, then this is like G2, then this one is like G3. You're breaking it into smaller paths. But you cannot, G cannot be a function on that interval because by definition it always has to be rescaled. So G subscript J, that's just the rescaled version. So then the original path that we have in the beginning, it's just the juxtapositions of all of these, all of those subpaths, of all of those n subpaths, right? The full path is I guess I should say homotopic to. Maybe that would be a little bit better to say that G is homotopic to that. That G is going to be homotopic to all of those subpaths. That if you take all of those subpaths, you rescale them from 0 to 1, and then you take the juxtaposition, that would just be homotopic with G. Now, all of these are in the punctured, they're in the punctured circle. So all of these are arcs. All of these are homotopic to arcs. So this is going to be homotopic. The first one is going to be homotopic to some arc. You're going to have an arc. This is going to be homotopic to some arc. That's going to be homotopic to some arc, homotopic to some arc. All of these are homotopic to arcs, right? Because if you're in the punctured circle, it's contractible, and so all paths are homotopic. So you can make it be homotopic. So if G1, it begins, you see, it begins, well, I'd not write it down, but G0, it begins at 1, and it ends at 1. It's a closed path. These are not closed paths, but they're homotopic to arc. So this is going to be some arc that starts at 0, okay? So that's going to be some kind of arc. It starts at 0, and it goes up to some angle, whatever angle that is, call it alpha 1. And then you have G2. Now G2, it will begin where this one ends. So for G2, you're going to choose to be the same angle because you want them to match. You're going to choose that to be the same angle, alpha 1, and then it goes up to another angle called alpha 2. And then this arc, it begins where this one ends, so you can choose the starting angle to match with the previous one. So this is alpha 2, alpha 3, and it kind of just continues like this, alpha n minus 1. And now you see what happens. I mean, this is a fairly simple idea, that if you have one type of arc, right, you have one type of arc, alpha A0, 1, and then you have another type of arc from, this is one arc, and you juxtapose it with another arc from alpha 1 to, let's say, alpha 2, you can just say that this is going to be homotopic by going directly from 0 to alpha 2. So if you have two arcs that are right next to each other and they share that common angle, you can then combine them by a homotopy and then say this is the same thing as alpha 0, alpha 2. But then you have an alpha 2 there and you have an alpha 2 there, and you just combine them again. So in the end, what's going to happen is when you combine all of these arcs together, by the way, these arcs can go in opposite directions. It's possible that maybe the first arc moves like this, and the second arc, it will start at the same angle, but maybe it moves in the opposite direction, like this. And then the juxtaposition arc would be moved back. That's okay. I mean, that's fine. You can still do this. So in the end, when you juxtapose all of these arcs together, you're going to get an arc that begins at 0 and it ends at alpha n, whatever this is. And whatever that is, this is an arc. You're going around. Whatever that is, this has to be a multiple. That has to be a multiple of m. That has to be a multiple of m, because the G itself is a closed path. That's a closed path. So if you start at 0, wherever you end, it has to be something that closes back. So it has to be. So the final angle has to be a multiple of m, and then whatever that is in the end, the arc of going around m times, that's going to be homotopic to f to the m times, because you're going around m times. So we've shown that G is homotopic. So this is sort of like the generator loop. This is the loop where every other loop is homotopic to, provided you take the correct number of juxtapositions. So this is actually the easier part of the argument, to show that every other closed loop must be homotopic to something like this. So that's kind of the basic idea. The basic idea is you subdivide the unit interval into these which are small enough so that the original path that is restricted to these smaller subintervals omits either one of the points +1 or -1, and then you're in the punctured circle, and whatever this is, it's homotopic to an arc. So that means that you can take the original path, break it up into these subpaths that are juxtaposed together, and then replace all of these by arcs. You know they're homotopic because each of these is in a contractible space. And then when you just put all of the arcs together, that gives you the original loop where you go around a certain number of m times. So that is the way the argument goes. So it actually is more difficult to justify the invariance, the homotopy invariance of the winding number than it is to show that every loop is homotopic to some power of this basic loop that we have here. So when you look at this, you might be worried. Like, you might get worried. You might look at it and say, this was really hard, and that was really hard, just to compute the fundamental group of a circle, of just a circle. I mean, can anything get simpler than a circle? If it's this hard to compute the fundamental group of a circle, what hope is there to come to, let's say, compute the fundamental group of a torus or more complicated spaces, like we talked about the Klein bottle and things like that? So the part which is really strange, so strangely, a special argument is used only for a circle, and other spaces have computational rules to make it easier. But so that's like the really strange part about the fundamental group. It takes an enormous amount of effort to determine the fundamental group of a circle and justify that. But somehow, once you know it, finding the fundamental groups of the other spaces we're going to talk about is just going to be a lot easier. It's like, it's really strange that it works out like that. So if you look at this and you say to yourself, this is really difficult, how can we possibly have any hope of finding fundamental groups of more complex spaces? You're going to see that there's methods that you can use there that you cannot do for a circle. So a circle is somehow special, and it has its own very individualized kind of argument for it.